So while preparing my talk, I found it hard to imagine what would be the profile of the audience today, right? The Swiss math community is made out of mathematicians and physicists, and so I decided to put a bit of emphasis on certain notions, certain mathematical notions that I think everyone can understand. And the core, well, actually my main research will be presented perhaps at the end if I have time, but I first want to present those very beautiful results. And so the first part of my talk will be based on some review that has been written recently by Monin and Karanenas in Lausanne. And then at the end, I will go back to my own research. Okay, so to start with, the first point is to symmetry. And I think in the room here, we all have very good reasons to study symmetries. Well, I'm a theoretical physicist, so I study them in the context of quantum field theory. And for us, they are very important because they correspond to conservation laws of charges, right? Each symmetry has a corresponding charge, and it is conserved. And those are very important results for our understanding of particle physics or pretty much anything. And so we broadly classify them into two categories, right? The first one are called internal symmetries, and they act on quantum fields themselves, right? Those objects that we use to describe particle interactions and stuff like that, right? And the other sort of symmetry act on the space-time coordinates. So in this talk, I will be focusing on Minkowski space. So Minkowski space is just flat space with a specific metric. So in this case, it would be plus, minus, 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 right? So the time component has a different sign than the rest. And the basic ingredient that we usually put in a QFT is the requirement that it be invariant under Poincaré group. And Poincaré group is just a historical name for the group of isometries of Minkowski space, right? And so this implements by default Einstein's special relativity principle. And so this is something we really want to do, right? But nothing prevents us from adding more and more symmetries in the system. So either internal symmetries or geometrical ones. Right? And a fairly natural enlargement of the geometrical symmetry that the Poincaré group is the conformal group. And the conformal group is just, it refers to the coordinate transformations that leave the metric invariant up to a rescaling factor, right? So it preserves the shape locally, but it might rescale the metric. And so it happens that it actually turns out that the conformal group is fundamental for many different reasons. It's a key ingredient in the construction of string theory. If you know what an RG flow is, those are the conformal group is very important to understand the fixed points of the flows. Phase transitions are appropriately described by conformal theories and stuff like that. So they are very important, and it's very natural to consider them and to study them. It's a very important problem. And so the algebra, the conformal algebra, is composed by the generators of Poincaré, right? So those are the rotations in Minkowski space, right? Those are translations, and then we have dilatations, which is just the action of zooming in or zooming out, right? Rescaling the metric simply by a factor. And there is also an extra set of generators, which we call the special conformal transformations, KMU. And if you require your theory to be invariant under the conformal group, it happens to be that it is immensely constrained, like so much constrained that actually the problem of solving or computing anything in a CFT, in conformal field theory, reduces to the problem of computing a set of building blocks, which we call the CFT data. And so accessing those data, right, those building blocks, is a fundamental problem in theoretical physics. And there has been many different techniques developed in recent years, and I will try at the end of my talk to present one of such techniques. And in particular, I want to focus on a subset of those building blocks, which are given by the eigenvalues of the dilatation operator. So the response of my quantum field theory under rescaling of the metric is characterized by the set of eigenvalues of the operator G, and I will call them the conformal dimensions delta. Okay. And we'll also talk about the non-relativistic avatar of this construction, because it has very surprising features, and this is actually the reason of my title for my presentation. But you will understand that in a couple of minutes, hopefully. So the idea would be first to explain how and why we can derive or find an algebra automorphism in the conformal algebra. And so if we find an automorphism, it means that we have, well, two different ways of looking at the same problem, right? One is the original problem, computing the eigenvalue spectrum, the dilatation operator, for instance. And now we have, if we find an automorphism, it means that I just shuffled the generators among themselves and I preserved the structure, right? And so I a priori have a new way of looking at the same problem. And so this new way of computing things might be harder than the original problem. So in this case, it would be useless, right? But well, as you can guess, right, I wouldn't be talking about this if it was not useful. So, so let me, I will first review this notion of algebra automorphism, and then try to make sense of it in the context of quantum field theories, right? How do they act on quantum fields, and what are the consequences? And then hopefully, if I have time, I'll try to tell you how to extract some knowledge about the conformal dimensions in a very broad sense, exploiting these properties. Okay. And so, yeah, the first 2 points of my talk will be based on this paper. There's this very nice review that appeared last year, and then I will jump into more results. Okay. So I can just simply give you the conformal algebra, right, which is very simple to derive, and so you can find it in any book, basically. And well, the details here are not super important, but you might have recognized, for instance, the Lorentz algebra here, and here you could add the translations. So this is Poincaré group, Poincaré algebra, right, and then the rest. And so the task here is to write a linear combination of those generators in such a way that my newly defined generators have the exact same computation relations, right? This is a Lie algebra automorphism. And well, you could do that. Modulo some subtleties, you could all here find some automorphism, but I will just tell you the answer because it's very simple. And again, we don't care so much about the details here, but it exists, and that's the upshot, right? And there is an automorphism in the conformal algebra. But now the question is, how do I make sense of this property in the context of quantum field? And so I can look at how my generators act on the field, right? And typically, well, I wrote here the relationships, which are also basic things that you find. But for instance, if we look at the way translations act on fields, you know, it is given by the partial derivative, right, in the direction of the translation. And so now, if you write the same computation relations with the bar here, right, we what we call a translation in the original problem is not the same as what we would call a translation in the other side of the automorphism, right? This P will not be the same, so it translates in a different coordinate system, right? And the two are related by conformal transformations, but still it's a non-trivial fact that we have two descriptions acting on two different spaces, right? But it's equivalent in the end. And so if you try to relate carefully the two coordinate systems, and I'm skipping a couple of details here, the conclusion will be the following. The spectrum of eigenvalues of the dilatation operator in Minkowski space, perhaps here I should have put 1, d minus 1, but anyway. So the spectrum of eigenvalues, the dilatation operator in Minkowski space is isomorphic to the spectrum of eigenvalues of the Hamiltonian on the cylinder. And by cylinder, I mean this manifold here, right? So this is my new way of computing those part of the CFT data, right? I can just compute energy levels on the cylinder. And we have many different techniques to compute energy levels, right? There's the Legendre transform of the Lagrangian. So if you have a Lagrangian description, it's fairly straightforward. Okay. But before proceeding, I want to also discuss the case of the non-relativistic equivalent of this story. And the non-relativistic conformal group is called the Schrodinger group, right? And again, you have a bunch of commutation relations. We don't really care about the details here. Those are, again, the rotations in d-dimensional space. Those are the translations, the Hamiltonian here and stuff, right? And there is just one extra feature that I want you to notice here is this generator Q here, which is a central charge. It characterizes the particle number of the theory, the number of particles in my system when applied completely to a quantum field theory. Okay, and so again, can you find a linear combination of those generators such that the commutation relations are preserved? And that's the question, right? And a priori, there is no reason that such a property also exists in this case, but it happens to be the case. Okay, so there is an automorphism that allows us to look at the same problem in a new way. Okay. However, the consequence, if you try to look at this automorphism in the context of quantum field theory, you look at how the generators act, again on the fields, you will see that this is the time translation operator acting as a partial derivative, the same for translations and stuff like that, right? And again, you have to make sense of these two coordinate systems, right? You could put bars here, bar, bar, bar. And so this means that we are translating time and space in a different coordinate system. And so what it is, how do you make sense of that? And here there is a bunch of details that I also cannot show. But the upshot is the following, which is very reminiscent of the previous one. But it's a little bit surprising, I would say. So the spectrum of eigenvalues of the dilatation operator in flat space, right, is isomorphic to the spectrum of eigenvalues of the Hamiltonian, right? So the energy levels of the Hamiltonian when coupled to a harmonic. And so it means that it's just this function x squared. So I just have like a potential that goes like a parabola, and I restored some constants here, which we don't really care about, right? But so now the system is trapped in a confining potential, and if I manage to compute the energy levels of this system, then I will get for free the spectrum of eigenvalues of the dilatation operator. So the conformal dimensions, and those are part of the CFT data, and it's very useful it's actually fundamental to solve this problem. But so it might or might not ring a bell at this point, right? But the fact that we have to study the energy levels of a quantum system, of a non-relativistic quantum system put in a harmonic trap, might be reminiscent of your quantum mechanics class, and actually, and this is the justification of my title, this is being measured in the lab directly. So this is exactly the setup that people use in cold atom experiments to compute, and they do measure the energy levels of the system. So here is a picture of what they actually do. So this is, you should imagine this harmonic potential in 3 dimensions. So it's actually a ball or a cloud of particles, right? And here they even excited it a little bit, so you have vortices forming here. And this is like a very striking feature. It's a superfluid, and it has very nice properties and stuff. And so we are actually talking about this, exactly this, and measuring the energy levels of this system here actually provides us with a way of computing the abstract CFT data of my theory originally. So I think this is an amazing completely accidental link between a very abstract theoretical goal and what people have been measuring in the lab for the past 40 or 50 years. And as an experiment, it's very exciting, I think. So now I have a couple of minutes left, I think, so I can try to tell you how we approach treating this problem. And in particular here, you cannot really visualize the particles, but there are like up to 10, 5 or 10 to the 6 particles. So it's a system with a large particle number. And the particle number was written Q before. I told you to pay attention to this generator Q, right? And here it's very large. And generally speaking, we expect that certain limits, where certain parameters take a very large value, may be something simplified. And actually, at the University of Bern, Susan Reffert and Domenico Orlando and other people, collaborators, actually started a nice and ambitious program a couple of years ago to compute the CFT data of CFTs when some charge takes a very large value. So this is exactly the same setup. And actually here, the nice feature is that it is observed in the lab. And so we can actually compare with experiments. So how does that go? And for that, I need to jump into more physical stuff. Into more physical stuff. So perhaps I will lose part of the audience, but I just have 2 minutes to tell you that. So I'll just quickly go through the steps. So we use effective field theory techniques, right? And effective theory techniques is a way of describing the low energy regime of a theory without knowing all the details. When we say the details, all the details, this means the high energy behavior of the theory. And you might have heard of Goldstone mode. So those are the degrees of freedom that are left in the low energy regime. And so this whole system can be described appropriately in the context of effective field theories, provided that the charge is very large. And the reason is that we want to have an expansion parameter, just like a Taylor expansion, right? If I tell you that 1 plus x is supposed to be describing the exponential of x, right? I'm obviously missing some terms, but hopefully I'm not too wrong because x might be small. And if I have a good reason to believe that x is small, then it's a fair approximation. And this approximation happens to be available if the charge is very large, as I said. So here it's the case. So we have 10 to the, as I said, 10 to the 5 or 10 to the 6 particles in this system here. So the upshot, and I'm going to jump to the conclusion so that I don't bother you with details, is the following. So the lowest eigenvalue of the conformal dimension, of the dilatation operator, so this delta, which I call delta Q, in a sector of fixed charge Q, is given by an asymptotic series in powers of Q. And this is a universal property of theories that are described by this regime, this low energy regime. And the price to pay to have this universality is that we we don't know those coefficients A1, A2, and A3, which are called the Wilsonian coefficients, if you know the Wilsonian. And so this is the conclusion you would reach in the relativistic case. But in a non-relativistic case, there is even more stuff going on and even more structure happening in the expansion of the conformal dimension in terms of Q. And the final answer, which I will just jump to, is the following. So the full expansion of delta Q, which I found last year, is the following. So it has the exact same asymptotic series as we had before in the relativistic case, but we have extra stuff here, extra structure arising from boundary effects and stuff like that, which I will not talk about. If you want to have a concrete example of how it goes in d equals 2 or d equals 3, then I wrote here the expansions. And there's a lot to say about these, but unfortunately I don't have much time, so I will just conclude with my Outlook slide. And thank you for the attention.
Thank you. Questions? So these systems of cold atoms are supposed to be described by conformal field theory. How can one see that?
So you might have heard of the BCS Bose-Einstein condensate crossover, perhaps not. So it's, if you trap fermions in this harmonic trap, you can tune the interaction strength between them, right? And so they would exhibit different properties depending on the interaction strength. And this can be tuned experimentally with an external magnetic field. So people have a lot of control over that. And on one very far side of the regime, well, of the interaction scale, you would be in what we call the Bcs phase, which is form coupled pairs and stuff like that. And on the other side, they condensate and they actually form like bosonic molecules. So fermions pair up together, and they effectively are described by bosons, right? So those are the two extrema of the interaction range, right? And in the middle of this axis here, there is a specific point where all the scale disappears, and we call this the unitary regime. And so the unitary Fermi gas is known to be a conformal, a non-relativistic conformal.
Okay, so if there are no more questions, let's thank the speaker again.